Hi, everyone, and welcome to week 7 of Introduction to Logic. Today, we are going to look at 5 new rules of replacement on top of the 5 rules of replacement that you looked at last time. Without further ado, let's dive in. The first of the new rules of replacement is transposition, abbreviated TRANS. This is a fairly easy rule to understand. In fact, it sort of mirrors the internal reasoning of the modus tollens rule. If you have a conditional like P implies Q, that's equivalent to not Q implies not P. And I think you can see why this is similar to modus tollens. In modus tollens, if you have a conditional P implies Q, if you have the negation not Q, you know you can get not P. That's exactly what's going on here. If you have a conditional P implies Q, that means if you know not Q, then you can get not P. So you can rewrite a conditional, reversing the order of the antecedent and the consequent, as long as you place negations in front of both terms. So P implies Q becomes not Q implies not P. And of course, like all equivalence rules, all rules of replacement, this works the other way around. If you have a statement like not Q implies not P, you can rewrite that on a subsequent line of the proof as P implies Q. So this is a fairly easy rule to understand. The next rule we're going to look at is material implication. Sometimes it's just called implication, abbreviated IMPL. And this rule says this: if you have a conditional, P implies Q over here on the left, that's going to be equivalent to not P or Q. And vice versa. If you have a disjunction like not P or Q, you can convert that to P implies Q. Okay. The third rule is a fairly easy to understand rule. In fact, this is the first rule you have that lets you do something with the biconditional symbol, the triple bar symbol there on the left. If you have a biconditional, P is equivalent to Q, that's going to be equivalent to, in fact, this is why it's called a biconditional in the first place. That's going to be equivalent to P implies Q and Q implies P. So a biconditional is like a conditional that goes both ways. P implies Q, but Q also implies P. And that's what we have going on here in this first row. There's another version of equivalence. If you have a biconditional, P is equivalent to Q, I want you to think about what this means. If P is equivalent to Q, that means they have identical truth values. So that means that either P and Q are both true or P and Q are both false. So either P and Q or not P and not Q. And that's what it means for the two terms P and Q to be equivalent. They have identical truth values. Either they're both true or they're both false. So both of these two versions of this rule are called equivalents. Okay, the next rule, exportation, is fairly easy to understand. If you have a conditional like this, if P and Q, then R, that's going to be equivalent to if P, then if Q, then R. And I think you can see why. If you have a conditional like P implies Q implies R over here on the right, that says if you know P, then if you know Q, then you get R. So if P and Q are both true, then you'll get R, and that's what you have over here on the left. So this is a fairly easy rule to understand. I think the reasoning is fairly straightforward. And again, like all equivalence rules, this rule goes both ways. It's also worth reiterating that what distinguishes rules of replacement or rules of equivalence from the first batch of rules you learned, what are called rules of implication, is that you can apply these replacement rules not just to entire lines, but to parts of entire lines if you need to in the context of a proof. And finally, the last new rule is called tautology. And that says if you have a statement P, that's going to be equivalent to either P or P. And I think this is obvious. It's so obvious it should be called a tautology. If P is true, then either P or P is true, and vice versa. If you know that either P or P is true over here on the right, that means P has to be true on the left. And the same thing with conjunctions. If P is true, then somewhat obviously P and P is going to be true because both of those two terms will be true. And again, somewhat obviously, if P and P is true over here on the right, then you know that P has to be true over here on the left. So tautology is a fairly straightforward rule. Without further ado, let's go ahead and dive in and look at some proofs using these new rules. I'm going to try to keep this video as brief and on point as possible to give you as much time to work on your homework exercises this week, given that the homework exercise for this week is a fairly lengthy assignment. Okay, The first proof has two premises. If S and K, then R. We're given that K is true on line 2, and we're trying to show that S implies R over here on the right. Now, the first thing I notice is that the first statement, S and K implies R, seems to match one of the new rules. In fact, let me back up here. I'll put it back on the screen. That seems to match the form of exportation right here. So my guess is we're probably going to do something with exportation in this proof. Although, what I see is that, let me try to do this on scratch paper on the right. I see that if I did exportation as it is, I would get S implies that K implies R, which isn't actually that helpful because we don't have S on its own line. We have K on its own line here in line 2. But if I do commutativity on line 1 first to convert it to K and S implies R, and then do exportation, I'll get K implies that S implies R. And that's really helpful because we know that K is true on line 2. So let's do what we just said we would do over there in our scratch paper on the right. We'll add a new line, line 3. We're going to do commutativity just on this antecedent to line 1. So we're going to convert line 1 to K and S implies R. Line 1 by commutativity, COM. Then we said that if we did exportation, we would get K implies that S implies, let me make that a little cleaner for you. We said we would get K implies S implies R from line 3 now by exportation. And the rest of this proof should be pretty straightforward. Line 2 tells us that K is true. So by according to modus ponens, we know that S implies R from lines 2 and 4 by modus ponens. And we're done. So like all equivalence rules, sometimes you'll have to do what I consider to be fairly obvious steps, but necessary steps in order to be able to apply subsequent steps correctly. Here, you had to recognize that you had to do this commutativity step on line 3 in order to be able to do the key step here, which is the exportation step on line 4. Okay, let's go ahead and move on. Okay, in this proof, we are given two premises. T implies that either F or F is true. 2 tells us that it's not the case that F and F, and we're trying to show the conclusion not T follows from that. So the thing that stands out to me here is the repetition of the term F. In the consequent of line 1 right here, we have F or F, and in line 2, we have F and F inside parentheses here on line 2. And whenever you see that kind of repetition, something or the same thing, something and the same thing, you should immediately start to think that tautology rule, because the tautology rule will let you collapse those repeated terms down into a single term. So let's try that. I'm going to rewrite line 1 as T implies F. That's going to follow from line 1 by tautology, T-A-U-T. What I've done is just collapse this F or F into a single term, F. Okay? And we're going to do the same thing on line 2 now with that repeated F inside the parentheses. So if we collapse F and F, we're just going to get F, and there's a negation out in front. So line 2 is going to convert to just not F from line 2 by tautology. Okay? And now the rest of this proof is really straightforward. Line 3 says T implies F. 4 tells us that F is false, and this should be a review for you guys at this point, but we know from that T has to be false, the negation of that antecedent on line 3. That's going to fall from line 3 and line 4 by modus tollens, MT. So here, this proof wasn't too bad, and there are other ways to do this proof. This is probably the most elegant way to get rid of those repeated F's inside line 1 and line 2. Once you use those tautology steps in line 3 and lines 3 and 4, the conclusion follows pretty naturally from those premises. Okay, next proof. We're given two premises. S is equivalent to Q. Line 2 tells us that S is false, and the conclusion is that Q is false. Now, in a way, this argument is obviously valid. If S is equivalent to Q, and we know S is false, then by definition, that's what equivalence means. Q would have to be false as well, because Q has to have the same truth value. But the challenge here is to show this using a natural deduction proof. So finally, we have a rule that lets you break apart a biconditional. And I'm going to use the first version of the equivalence rule to convert it to this. If S is equivalent to Q, that means S implies Q and Q implies S. That's going to follow from line 1 by equivalence. Okay. And I think from here, it should be fairly straightforward how to go about getting the conclusion. The conclusion is not Q, and we know that S is false. So if we could get this part of that conjunction, Q implies S on its own line, then we could do modus tollens and get not Q. So how do we go about getting the right side of that conjunction on its own? Well, first of all, we have to use commutativity to get that term in parentheses on the right on the left side of that conjunction. So let's rewrite line 3 as Q implies S and S implies Q. Line 3 by commutativity. And now, once Q implies S is on the left, we can simplify line 4 to get Q implies S. Line 4 by simplification. And on line 6 now, if we know S is false, from line 5, we know that Q is false as well, not Q. That's going to follow from line 2 and line 5 by modus tollens. And even though there are 2 versions of the equivalence rule, you actually really only need one. This is by far the most common version of the equivalence rule, the one I would encourage you to use. There will be instances where the other version of the equivalence rule will yield shorter proofs, but by far, this is the most common use of equivalence, to take a biconditional like S is equivalent to Q and convert that to S implies Q and Q implies S. I should say, while we have this proof up, this is actually how you go about proving a biconditional as well. If you need to demonstrate that S implies Q, if that were the conclusion, one way you could go about that would be to prove these 2 conditionals, that S implies Q and Q implies S, and then apply the equivalence rule to convert that to a biconditional. So again, like all equivalence rules, the equivalence goes both ways. S is equivalent to Q is equivalent to S implies Q and Q implies S. But if you know that you have 2 terms that imply each other, you can convert that to a biconditional using the equivalence rule as well. Okay, next proof. Line 1 tells us that F implies B. Line 2 tells us that B implies J, and we're trying to show the conclusion F implies J. Okay, line 3. So the first thing I notice here is that line 2 looks like one of the forms for exportation, the exportation. I'll just write that off to the side. And if I apply exportation there, I will get this statement. B and B implies J. And that's going to follow from line 2 by exportation. Now, this is a really good result because we have this repeated B term, a conjunction with both of the terms being the same, B dot B inside parentheses. By the tautology rule, I can eliminate that conjunction and replace that parenthetical expression with that just the term B. So B implies J, rewriting line 3 to eliminate that conjunction. And that is going to follow from line 3 by tautology. And the rest of this proof should be really straightforward. Line 1 says that F implies B, but now our new line 4 tells us that B in turn implies J, with B being the middle term. So we know that F implies B, B implies J. That will give us F implies J, which is our conclusion. And that would follow from line 1 and line 4 by hypothetical syllogism. Okay, so this is a pretty straightforward proof. In fact, I could actually do this another way. I'm going to take just a moment and redo this proof, showing another approach you could have taken. It's similar, but this goes to show there's more than one way you can approach any given proof. What I could have done Instead of applying tautology on the rule that we got from exportation, or the line that we got from exportation, we actually could have used tautology to introduce the conjunction rather than eliminate the conjunction. So for example, on line 1, where F implies B, I could have done something like this. F implies B and B. That would follow from line 1 by tautology. Excuse me. There we go. And the rest of the proof would look really similarly. On line 2, if we applied exportation, we'd get B and B implies J from line 2 by exportation. And now we can apply hypothetical syllogism in a similar way, but with B and B being a complex middle term. So for example now, on line 3 tells us F implies this expression in parentheses, B and B. Line 4 tells us that that very same expression, B and B, implies J. So F implies J by hypothetical syllogism from lines 3 and 4. Slightly more complex way to do this proof, but it would have worked just as well. And this is true for most proofs. As we get more and more rules, you'll see that there's going to be more than one way you can approach any particular proof. Okay. Before we get started on this proof, let's take a look at the premises and the conclusion and see if we can talk through what we're probably going to do. Lines 1 and 2 are both conditionals. Line 1 says that Q implies that expression in parentheses, F implies A. Line 2 tells us that R implies another expression in parentheses, A implies F. Line 3 says Q and R are both true, and that's great because we can probably simplify both of those terms in line 3 and get the antecedents to those conditionals in lines 1 and 2. And that should all be reviewed from the rules of implication. We're trying to prove a biconditional. And to prove a biconditional, if we're trying to show that F is equivalent to A, one way we can do that, I'm just going to start a little scratch note here on the right of the screen. If we can show that F implies A and A implies F, then we will have shown that F is equivalent to A by the equivalence rule. And very happily, it looks like once we do those modus ponens steps I just described, we'll get F implies A and A implies F. All we'll need to do is conjoin those two statements together and apply the equivalence rule to prove that that biconditional is true. So with that in mind, this should be a fairly straightforward proof to do. Let's start right here. Let's add a new line, line 4. Right off the bat, we're going to simplify line 3 to get Q. So line 3 by simplification. On line 5, in order to get R on its own line, we first have to apply commutativity. So R is on the left side of that conjunction, R and Q. And that's going to follow from line 3 by commutativity. And then we're going to simplify and get R on its own line. So line 5 by simplification. This should all be review and fairly mechanical and straightforward. Even if you didn't have any idea how to approach this proof, you should probably simplify to get Q and R on their own lines. Anytime you see a conjunction, simplifying them is never going to be a bad idea. Okay, once we have Q and R on their own lines in line 4 and 6, we can apply modus ponens steps together with lines 1 and 2. So from line 1 and line 4, we're going to do modus ponens and get F implies A. Modus ponens from line 1 and 4. And we're going to do the same thing with lines 2 and 6. That will give us A implies F. Modus ponens from line 2 and 6. Okay. Once we have these two conditionals, F implies A and A implies F, we said that all we needed to do over here in our scratch paper on the right was conjoin those two conditionals together and then apply the equivalence rule. It's going to take us 2 more lines. So we're going to get F implies A and A implies F. So that's conjunction from lines 7 and 8. And now that we know that those two terms imply each other, F implies A and A implies F, according to the definition of a biconditional, the equivalence rule, that means F is equivalent to A from line 9 by the equivalence rule. So not too bad, but you had to recognize that you're going to need to use the equivalence rule to build a biconditional by proving the conditional in both ways, proving first that A implies F, showing that F implies A, and then conjoining those two conditionals together and applying the equivalence rule. That's the definition of a biconditional. It's like a conditional that goes both ways. The two terms imply each other. Okay, next proof. Okay, we're given two premises. The first premise says that B implies G and F implies N. Line 2 tells us it's not the case that G and N, and we're trying to show not the negation, excuse me, of B and F. It's not the case that B and F are both true. Okay, what I notice right off the bat is that the conclusion looks like something I could get by a De Morgan's rule step. And it also looks like I can apply a De Morgan's rule step to line 2. And my guess is we're going to have to do both of those things. And line 1 is the conjunction of two conditionals. So I'm going to be on the lookout for a constructive dilemma step somewhere. With those in mind, let's go ahead and dive in. Okay. Line 3. I'm going to go ahead and apply De Morgan's rule on line 2 because I think that's a fairly obvious first step. So we're going to get the negation of G or the negation of N, not G or not N, from line 2 by De Morgan's rule. Now, the next thing I notice here is that these two terms, not G and not N, are actually really similar to what I see up here in line 1. This is starting to look like a constructive dilemma, except I don't have the antecedents of those conditionals. I have the consequence of those conditionals in that disjunction on line 3. So in order to be able to do a constructive dilemma step, I need those G's and N's to be on the left side of the horseshoe. I need them to be the antecedents of the conditionals. And I do have a rule, transposition, that lets me flip around the order of a conditional as long as I place a negation in front of both terms. So I can actually rewrite line 1, rewriting each of those two conditionals inside parentheses, reversing the order of them as long as I introduce some negations. And because there are two of them, I have to do it in two separate steps. So I'm going to apply transposition right here, just on that on that conditional in the parentheses on the left side of that conjunction. So if I rewrite that, I'll get not G implies not B. And then I'm going to rewrite the rest of the statement and leave it exactly as it is, because this has to be a separate step. F implies N. So I haven't done anything there. That's going to follow from line 1 by transposition. Okay. And then I'm going to do the same thing right here, reversing the order of that conditional, again, introducing negations in front of each term. And I'm going to rewrite the left term exactly as it is. Not G implies not B. And here's where I'm going to apply transposition again. Not N implies not F. So line 4 by transposition. Okay. Now, happily, I'm going to indicate this in another color just to make this really clear. Happily now, I have a disjunction here on line 3 that has two terms, not G and not N. On line 5, I have the conjunction of two conditionals, and the antecedents of those conditionals correspond to those two terms in the disjunction in line 3. So this means I can finally now do my constructive dilemma step that I thought I might be able to do. And so just to talk through the reasoning, if one of those two antecedents, not G or not N is the case, we know that one of the two consequents, not B or not F, would have to be the case. And that's what I can get on line 3, not B or not F. And that's going to follow from lines 3 and line 5 by constructive dilemma, CD. And we're very nearly done with this proof. Notice now that the conclusion is the negation of B and F. And if I applied De Morgan's rule to that, we would have what we have on line 6, not B or not F. So I can get the conclusion just by De Morgan's rule, the negation of B and F from line 6 by De Morgan's rule. And we are done. So the key here was recognizing that you need to do these transposition steps on lines 4 and 5 before you can apply that constructive dilemma step on line number 6. Not a terribly difficult proof, but if you didn't recognize that, you might be stuck. Okay, so this is a fairly interesting proof. We only have one very short premise, just the letter T, and we're trying to show that if S is the case, then T is the case. Now, in a way, this is pretty obvious. If T is true, then it follows that if S is true, T would have to be true because T is already true. But the challenge is to show this using a natural deduction proof. And I can guess that because S is not contained in the premises, we're probably going to have to do an addition step somewhere. The question is how to get started. How to use addition? What do we do? So what I can do, again, it's very helpful with the rules of replacement to start out by working backwards a little bit. If we're trying to show that S implies T, I'm just going to do this as scratch paper off to the right. We have a rule that lets you convert a conditional to a disjunction. S implies T would be equivalent to not S or T by the implication rule, IMPL, what your textbook calls material implication and abbreviates IMPL. And this is really happy now because if we can get not S or T on its own line, we could apply implication and convert it to that conditional we need, S implies T. Well, how can we get not S or not T? Well, we already have T. So if we could add a not S onto that, something like this, T or not S, then we could use commutativity to get this line, not S or T, and finally use implication to get the conclusion. Since we already have T, working backwards allowed us to see what we needed to add on to that letter T using the addition rule. We didn't just need to add S, we needed to add not S. So now this proof should be almost a no-brainer. This should take no effort whatsoever. Once we know we need to add not S onto T. So line 2 will be T or not S from line 1 by addition. And that should be review at this point. We said we need to do commutativity, so not S is on the left, not S or T. That's going to follow from line 2 by commutativity. And we did that so we could set up an implication step. If we have a statement like this, not S or T, that's going to be equivalent to S implies T according to the implication rule. Now, if that's not obvious, I want you to pause here, look at the form for the material implication rule in your textbook, reverse the video a little bit, look at the form of that rule, and you'll see why this follows. So this follows from line 3 by material implication, IMPL. And we're done. A fairly short proof. But if you try to add just an S on T or S, you would be stuck and you wouldn't be able to get to the conclusion. So whenever you use the addition rule, you need to make sure you're adding on something strategically that will let you get to the conclusion you're trying to prove. And sometimes starting with the conclusion and working backwards using the rules of replacement can yield what exactly you're going to need in order to be able to reach the conclusion. Okay. This next proof has a couple of fairly intimidating premises. The first premise is O implies C and not S implies not D. Line 2 tells us that E implies D and not E implies not C. And we're trying to show from that that O implies S. Now, right off the bat, I don't obviously see how to get to the conclusion, but I do see that I have a fairly complex set of conditionals here. A couple of them have a lot of negations packed in, like the ones on the right side of those conjunctions in line 1 and 2. So I think I'm going to start by simplifying some of these terms out. And I may not need to use all of them, but I think doing so will probably yield the path to get the conclusion. So let's dive in and start adding some new lines. I'm going to start by reversing the order of these conditionals on the right side of lines 1 and 2 using the transposition rule and eliminating those negations. That may or may not be helpful, but I think it will probably yield what we need to do. So I'm going to rewrite line 1, reversing the order of this conditional here on the right side of it to be D implies S by transposition. Okay. I'm going to do the same thing on line 2 now. E implies D, I'm going to leave that portion alone, and C implies E from line 2 by transposition. So the next thing I see is that I've got a fairly complex chain of conditionals here. Because these conditionals are inside these conjunctions, I could simplify and get all these conditionals on their own line. And if I follow through the chain of reasoning, keeping in mind what I'm trying to prove here, I'm trying to prove that O implies S. And so if I start up here on line 3, I know that O implies C. On the second half of line 4, I see that C implies E right here. On the first part of line 4, I see that E implies D. And way back up here in line 3, I see that D implies S. So ultimately, if O is true, then S would have to be true. I just need to break apart these conjunctions on line 3 and 4 and apply a couple of hypothetical syllogism steps, and I should be able to get to this conclusion fairly easily. So let's do that. So first thing we're going to do is simplify to get O implies C from line 3. Line 3 by simplification. I'm going to do the same thing on line 4. E implies D from line 4 by simplification. Now this is where this is going to get a little tedious. We need to reverse the order of the conjunctions in line 3 and 4, so those conditionals on the right are then on the left side. So let's rewrite on line 7 and 8. We're going to rewrite lines 3 and 4, reversing the order of those conjunctions. So 7 will be D implies S and O implies C. Line 3 by commutativity. On line 8, we're going to get C implies E and E implies D. That's going to follow from line 4 by commutativity. Now we're going to simplify to get D implies S from line 7 on its own line by simplification. And we're going to get C implies E from line 8 by simplification. And I'm going to add a divider line, and we're going to keep going on the right here. Well, we said that O implies C, but C implies E. We can see that now on lines 5 and 10. So from that, we can get O implies E by hypothetical syllogism. So HS lines 5 and 10. Now line 11 says O implies E, but back on line 6, we know that E implies D. So from hypothetical syllogism again, we can get O implies D. That's going to follow from hypothetical syllogism line 6 and 11. Now we know that O implies D on line 12, and line 9 tells us that D implies S. So from yet another hypothetical syllogism step, we can get the conclusion O implies S. From hypothetical syllogism line 9 and 12. And we're done. We've shown the conclusion follows. So that wasn't too bad. I think the key was recognizing that you had to apply transposition to these to the conditionals on the right side of lines 1 and 2. And once you did that, the rest fell out pretty quickly. You know, commutativity steps, simplification steps, really easy rules, just a few instances of those, and a chain of hypothetical syllogism steps to show that that conclusion would follow. Fairly straightforward. Okay. So for this next argument, we're given 3 premises, not H implies B. Line 2 says not H implies D. Line 3 tells us it's not the case that B and D are both true, and we're trying to show from that that H has to be true. I think this one will actually be fairly straightforward as well. I see right off the bat that we can do a De Morgan's rule step on line 3. So let's do that. We'll get not B or not D. And that's going to follow from line 3 by De Morgan's rule, DM. Okay, what I see next, again, I'm gonna use a couple different colors here to make this really clear. The 2 terms that make up this disjunction, not B or not D, are really similar to what I have up here in the consequence of line 1 and 2, except that I've got negations in front of them in line 4. What I can do, though, I can use the transposition rule to reverse the order of the conditionals in line 1 and 2, introducing negations in front of both terms, and that will get not B and not D respectively as the antecedents of those new conditionals. So this will take a couple of steps, but I'm going to go ahead and crank that out. So we're going to apply transposition to line 1. That will give us not B. Here's where you have to be really careful. Implies not H. Don't lose track of your negations here. It's very easy to forget to introduce negations in front of both terms, even if that yields a double negation like it did here. So that's going to follow from line 1 by transposition. And we're going to do the same thing now on line 2. Line 2, we're going to convert to not D implies not H. Be careful of those negations once again. So line 2 by transposition. Okay, what I'm going to do next, I actually see a constructive dilemma already here. I see that line 4 is a disjunction, not B or not D, and each of those two terms implies something. Line 5 says that not B implies not H, and line 6 says that not D also implies not H. In order to set up a constructive dilemma, though, I need to conjoin those two conditionals together. So let's do that. So we're going to get not B implies not H in parentheses, and not D implies not H in parentheses. So that's a conjunction from line 5 and 6. Now I did that so I could do constructive dilemma. And if I do constructive dilemma here, I'm going to get, well, let me back up. I know that if one of those two antecedents is true, not B or not D, I know that one of the two consequents, not H or not H, would have to be the case. And that's what I can get on line 8, not H or not H, which is going to follow from line 4 and line 7 by constructive dilemma. But we know that if we have a disjunction where the two disjuncts are exactly the same, we can eliminate that disjunction, and that would just give us not H on its own line. And that will follow from line 8 by tautology. And one more step and we're done. We're trying to show that H is the case. We've just shown not H. So according to double negation, one of the rules from last week, we know that H would have to be the case. And that follows from line 9 by double negation, DN. And we're done. We've shown that H follows. Okay, so that one was pretty straightforward. I think the key here was recognizing that you could set up a constructive dilemma step, but you first had to reverse the order of these conditionals in lines 1 and 2, introducing a negation in front of each of the terms, the antecedent and the consequent, according to the transposition rule right here in line 5 and line 6. So if you need to reverse this video a little bit, go slowly and make sure you can understand why every one of these steps follows. Okay. Next argument. We're given two premises. S implies L and M. Line 2 tells us that M implies that L implies R, and we're trying to show that S implies R. I think this one will actually be pretty straightforward. Let's dive in. What I notice right off the bat is that if I apply exportation to line 2, I will get this. I will get M and L implies R. And I want you to understand why. Line 2 says if you get M, then if you get L, you get R. So line 3, if you get M and L, then you'll get R. I think the reasoning behind that step is fairly straightforward. That's going to follow from line 2 by exportation, EXP. Now, this phrase here, M and L, is really similar to what we have up here in the consequent of line 2, L and M. In fact, if we apply commutativity to one of those, then they'll be exactly the same. So I'm going to apply commutativity to the consequent of line 1, and that will give me S implies M and L. That's going to follow from line 1 by commutativity. And we're very nearly done. Line 4 says that if S, then we get this expression in parentheses, M and L. Line 3 says that very same expression in parentheses, M and L implies R. And we know from hypothetical syllogism that if S, then R. So this is a very short proof. This new line 5 is going to follow from line 3 and line 4 by hypothetical syllogism. But the key here is this step, recognizing that you needed to do this exportation step that follows from line 2. If you didn't recognize that, you'd be stuck and you wouldn't be able to work your way through this proof. Okay, next argument. So in this argument, we're given two premises. P implies that not E implies B. Line 2 tells us it's not the case that B or E, and we're trying to show that not P follows from that. Now what I'm going to do, off to the right here, I'm going to use a little scratch paper and work backwards a little bit. What I see right off the bat, the conclusion not P, I could get that if I could get the negation of the consequent on line 1. So if I could get it's not the case that not E implies B, then I could get not P by modus tollens and I'd be done. The question is, how do I get this statement that I just wrote on the bottom right part of the screen? Well, that's equivalent to this by implication. I can eliminate that conditional inside the parentheses, converting it to a disjunction as long as I introduce a negation in front of the antecedent. So if I could get that, then by implication, I could get the last line, and then I could do modus tollens and I'd be done. But of course, I can get rid of that double negation, and that's just equivalent to it's not the case that E or B, which I very nearly have. On line 2, I have this expression. It's not the case that B or E. And obviously, that's equivalent to the line below it by commutativity. So this is actually going to be a fairly short proof, but we're going to have to do a dance with some negations here. So on line 3, right here, we said that if we applied commutativity, I would get this. It's not the case that E or B. And that's going to follow from line 2 by commutativity. Looking back at our scratch work now, we said we need to introduce a double negation in front of that E. So we're going to leave this outer tilde alone, introduce a double tilde in front of line E, and leave the rest alone. And that's going to follow from line 3 by double negation. Then we said that by the implication rule, that's going to be equivalent to this. It's not the case that not E implies B. From line 4 by material implication, IMPL. That's when you might have to pause and go back and look at the rules and take a look about why that works. Okay, so now we have the negation of that consequent of the conditional in line 1, so we can do modus tollens and get the negation of the antecedent, which is just not P. And that's going to follow from line 1 and line 5 by modus tollens, and we're done. Fairly short proof. Okay, so that's the last proof I have for you for today. For your homework this week, make sure you get lots of practice on these new rules. This is a fairly lengthy homework assignment, so give yourself plenty of time. As always, reach out to me if you have any questions or concerns, or if you find yourself stuck on any exercises. I'm always happy to help. We could jump on a phone call or jump on a Zoom meeting and we can look at anything together. Otherwise, make sure you get me your homework exercise by the end of Sunday at 11:59 p.m. and have a great week. See you next week.